morning, everyone. My name is Ali Garrouch, and I'm from Kuwait University. The title of my talk is Automating Sandstone Acidizing Using a Rule-Based System. I have to acknowledge the contribution of two co-authors, Professor Haytham Lababidi from Chemical Engineering Department and Dr. Abdullah Ibrahim from the Petroleum Engineering Department, also from Kuwait University. I have to also acknowledge the funding of Kuwait Oil Company for this project. The details of this talk could be found at this citation in the Journal of Petroleum Exploration and Production Technology. Now, the outline of the talk is I will discuss the purpose of acidizing oil and gas fields in general, and in particular, sandstone acidizing stages, causes of failure of sandstone acidizing, and study objective, the expert system development, which is the outcome of this project, and the validation and then conclusions. Now, matrix acidizing is the injection of acid in reservoir rocks at a pressure less than the fracturing pressure. And in sandstone, in general, it's performed to reduce formation damage in the vicinity of the wellbore. Now, the damage types that exist are something like particle damage from drilling. In general, most of the damage types are associated with drilling. Particle damage from drilling, fines migration, clay swelling, polymer residue, also from drilling, bacterial infestation caused by the water injection, surfactant stabilized emulsions can be caused by drilling as well, and water blocks. The damage is in general somewhere 3 to 5 feet away from the wellbore. This is a donut shape of the reservoir configuration, so it's a near wellbore area, not far away, luckily. If the damage is far away, obviously hydraulic fracturing becomes more economical than acidizing. Now, the damage reduces, in general, the pressure at the wellbore and reduces the pressure profile in the vicinity of the wellbore. This is, if you like, pressure here in this axis. This is radius away from the wellbore. This is a wellbore. And if you guys know Darcy's law, I'm sure some of you do, can relate to that. This is nice to have a huge pressure drop for Darcy's law. You get more production. But the problem is this pressure here becomes so low, and this pressure at the wellhead is also low. So you can produce to the wellbore, but you cannot lift the fluid. You see? That's the dilemma. If the well is stimulated or acidized, the pressure will increase a little bit, and you get better performance in general. Now, how do we know that the well is damaged or has some skin? In general, we do what is so-called nodal analysis, and we match the reservoir performance of pressure versus flow rate with the tubing performance, and the intersection gives you the optimal rate. So if we are producing at flow rate less than this optimal, most likely there is either mechanical damage or damage somewhere in the reservoir. And therefore, this damage is usually, which is total damage or skin, we call it skin factor, is estimated from well test analysis. So as you see, it's a summation of many individual skin components or damage component. For instance, this could be damage in the gravel pack. This is damage due to high flow rates. This is slanting skin, inclination of the wellbore. This is partial penetration of the reservoir. And this is perforation skin, and this is the damage in the reservoir. So after obtaining the total damage from well testing, we have to find out what this value is. You may not have, in some occasions, this is equal to 0, and therefore, if you go and acidize the rock, it'll be a waste of time and resources. It'll be like somebody who's sick with the wrong diagnosis, give him the wrong medication. It might even make things worse. So it's extremely important at the beginning of this endeavor to do proper diagnosis of the type of damage and make sure that the damage is indeed in the reservoir and know exactly what type of damage exists, because the treatment will differ. This is an example from a well in the Middle East. If you are familiar, the gamma ray log here shows that we have a net pay of about 150 feet, which is extremely thick. And resistivity, the true resistivity log shows that the reservoir is filled with oil, but it's only producing 3,700 stock tank barrel per day, which is much less than the nodal analysis optimum value. And the reason is not really because it is damaged here, but rather because it is partially penetrated. So there is a partial penetration damage, but no damage inside the rock. Look here, the perforation are only in the upper maybe 30 feet or so of the reservoir. So when they went back and perforated the whole section, the production doubled or so. So this is a nice example where acidizing will not work, no matter how much acid you inject. Now, for the sandstone acidizing, we have 3 stages in general. This is the conventional acidizing process. The first stage is pre-flush. The second stage is the injection of the main acid, which is usually the mud acid, combination of 12% HCl and 3% hydrofluoric acid. And then this is followed by overflush and sometimes diversion for heterogeneous reservoirs. The pre-flush stage, and I'll go over this quickly, usually is meant to displace water, minimizing contact of hydrofluoric acid with sodium and potassium ions to avoid precipitation like sodium and potassium hexafluorosilicates, you see. And to remove also calcium carbonate, cement and material to prevent calcium fluoride precipitation. The main acid stage is usually a mud acid, this concentration, and this HF, and this combination here, HF reacts with fines, clays, and HCl, keeps pH low and helps to prevent secondary reactions. Now, there are traditional guidelines for this, and in general, the guidelines will tell you what type of acid you inject. For instance, 10% HCl, 3% HF here. The concentration will vary up to 3% HCl, 0.5% HF, depending on the permeability of the reservoir and the amount of clays, and sometimes even the type of clay. So what is the problem, therefore? You see? The problem is that when people apply these guidelines, the results are not always as expected. Indeed, the success rate, the global success rate of sandstone acidizing is about 30%, which means 70% of the jobs are failure. And these jobs, sometimes they cost between $50,000 to sometimes $200 per well. And imagine you spend $200 if you have a horizontal well, and you get bad results. It's not too pleasant to report this stuff. And as well said by Leonard Kelfayan, an expert in the acidizing area, he says with acidizing, and he means sandstone acidizing in particular, there are many more exceptions to the rules than there are rules. In fact, true success in acidizing is associated with a better understanding of these exceptions. See? So there are causes of failure as a consequence. If there is a huge failure rate, there are causes of failure. In general, the causes of failure are poor candidate selection, lack of mineralogical information, wrong acid design, sometimes wrong diagnosis of the type of damage that exists, use of inappropriate acid additives, insufficient iron control, formation of emulsions, and asphaltene sludge. And in particular here, some people are not careful sometimes with use of HCl and HF for non-paraffinic crudes. In general, when you inject them with HCl, they end up either causing rigid emulsions or asphaltene sludge, depending on the API and the stock tank asphaltene content of the crude. So see here, for instance, for the mud acid, different concentration, the injection of this mud acid with a highly non-paraffinic crude causes somewhere up to 30% increase in sludging, asphaltene sludging. And this is even exacerbated if you use only HCl alone, which is the case of the pre-flush stages sometimes. You get about 130% increase in sludge. That's a lot. And the problem is sometimes operation engineers are not really aware of these details, and they inject HCl when they should not inject HCl, and they end up plugging the whole reservoir instead of improving the performance of the reservoir. So I talked about the major defects or the major causes already. Now the objective is therefore of this study is to put a structured process that can design acidizing jobs and take into account the crude type or the compatibility between the crude and the acid, compatibility between the acid and the mineralogical composition, and the process should be damage fit. In other words, each damage type should have a different recipe for acidizing. So we want to build, and then we wish to automate this because there are too many rooms. It really becomes very perplexing task to do this. There are too many rooms, so it would be nice to automate this. So we thought to automate this structured process using a fuzzy expert system. Okay. Now, the system, the structure of the system has a pre-flush stage, a main acid stage, and a post-flush. But the new thing here is that we divided the pre-flush into formation oil displacement, formation water displacement stage, acetic acid stage, and HCl pre-flush stage. So the pre-flush became indeed 4 stages just to make sure that we scrutinize the process in much more details. And then we expanded the acid base that can be used. Otherwise, the conventional, if you recall, the conventional guidelines use practically most of the time the mud acid, which is a combination of hydrochloric acid and hydrofluoric acid. So we expanded that base to include fluoboric acid, phosphoric acid, acid chelating-based blends, which are carboxylic acids, and mud acids in general for very special circumstances. The advantage of phosphoric acid is that it can handle minerals like zeolite, which in general precipitate, give you gelatinous precipitate in contact with HCl, even at very low temperature of 75 degrees Fahrenheit. And acid chelating-based blends or carboxylic acids are very effective if the calcite content of the rock is high, and at the time you do have lots of clays. So you have the sandstone, which is mainly silica, but we say greater than 6% calcite content, and also some clays exist. The problem is the clays, you see. And erythorbic acid usually acts as a reducer. Okay? So I'll skip some of those, because I already talked about this. Now, this is the structure of the expert system. Like I said, there are 4 stages for the pre-flush, and then we have a main stage that has decision trees that will depend on the damage type. See, this is what people before did not pay attention to. It's like all damage types, they inject one acid. All type of diseases give them one medication, one type of antibiotic. Well, it might work if you are lucky, but for sure there are people who are allergic to certain types of antibiotics and might be dead when administered. So it's a similar situation here. We have to really pay attention to the type of damage or the type of problem in the rock and administer an acid recipe that corresponds to that type of damage. And then there is the overflush and diversion for heterogeneous material. So this is an example of stage 1 in the formation oil displacement. It is really meant to clean the rock from organic deposit before acidizing. And the formation water displacement is meant to condition the clays, make sure they don't swell before the rock is contacted by acid. And the acetic acid pre-flush is meant to handle the rock if you have lots of iron minerals like hematite, pyrite, chlorite, etc. HCl would be really a problem in that case. And then there is the HCl pre-flush, which is meant to dissolve the calcite material and prevent calcium fluoride in contact with hydrofluoric acid. And then there is the main acid stage decision tree, which will depend again on the damage type. You see, so we classified these damage types about 1, 2, 3, 4, 5, and 6. You have one decision tree, damage type 15, for instance, another decision tree. So those are the damage types that may exist. I think that there are about 17 or so. And we have a decision tree for each damage type. Okay? All right, so the expert system is available online. I don't think you will be able to get through unless you get permission. This is an old username and password. I don't think it will work if you. But this is the graphical user interface. It's very user-friendly, and the system will ask even people who are not really very familiar with the process of acidizing can get good results because the system will guide you through the questions. Here, are there whole mud losses? Yes or no? Are there any organic deposits? Yes or no? Then it asks for the concentration of different minerals that may exist in the rock: anthracite, hematite, magnetite, pyrite, siderite, etc. Chlorite, the types of clays, elite, feldspar, sodium and potassium feldspar. And then it starts giving the recommendations stage by stage. You see, it asks for the rock is naturally fractured or it has any calcite partial filling. The crude type, is it highly non-paraffinic or paraffinic crude? The API of the crude, the stock tank asphaltene. You see, the type of feldspar that exists, is it orthogenic or detrital? Is it part of the matrix or does it grow inside the pores of the rock themselves? All these details were not accounted for in previous acidizing job, and that explains the failure rate, you see. And then it asks for the damage type that exists, and according to this, it gives you the final outcome. Now, we tested the system with many fields from around the world: Nigeria, Indonesia, Kuwait, etc., and it gave excellent results, conformal to standard practice. And you can go to the details of the paper, which is over here, to see the results. In conclusions, we developed a web-based expert system for designing matrix acidizing of sandstone. The system helps automate a very perplexing designing task. The system can be easily upgraded with new scientific advances in the area, so it's always open for improvement. That's the advantage of putting stuff like this in expert system. And it accounts for compatibilities between the crude, mineralogical composition, reservoir properties, and acid types. And I thank you very much for your attention.